So to get started in 7.3, we're going to continue with trigonometric integrals, but we're going to use our trig functions in a different way. So at the very front of 7.3, there is a table that's going to suggest trigonometric substitutions to us, and then there are some triangles that correspond to the substitution that we're going to do. So a couple of comments about this table. In this table, it shows radicals and then some different expressions and recommends that we use a certain substitution and a certain identity. We can use these when radicals aren't present as well, so as long as any of the radicands are present, so what I mean by that, a squared minus x squared, a squared plus x squared, or x squared minus a squared, this strategy will also work. It's just, it's very potent and works very well at eliminating radicals, as we'll see. So these radicals can make it hard or impossible to do antiderivatives, and we will use this to help us get rid of these radicals. All right, so let's take a look at example number 1. So we wish to evaluate the following integral. So the integral from 0 to 1 of the square root of 1 minus x squared dx. So if we look at our table here, we're trying to find something that matches 1 minus x squared. So in this table, the a is playing the role of a constant or something that's a perfect square. 1 is a pretty simple one because 1 squared is 1. And so we're trying to find something of the form a squared minus x squared. Well, that puts us in the first row of this table. So anything of that form, our suggested substitution is x equals a sine theta. And the identity that we're going to need to use is one of the Pythagorean, is 1 minus sine squared theta equals cosine squared theta. So in this case, we identify that our a is 1 because we have 1 squared minus x squared. Our suggested substitution is we're going to let x equal to sine theta. So one thing we'll notice, this is different than substitutions we've done in the past. In the past, when we picked u to be something that was present in the integral. So this is often referred to as an inverse substitution, as we're letting the variable we have equal a function of another variable. We're still going to do the same thing, which is we need to calculate our new differential. So if we take our derivative, dx is equal to, the derivative of sine is cosine theta d theta. So this tells us that if, or when we evaluate our integral, that we're going to replace our dx with cosine theta d theta. So we have the integral of the square root of 1 minus x, so that's going to be sine theta quantity squared, and then we replace our dx with what it is equal to, in this case, which is going to be cosine theta d theta. So we've now transformed this integral once again into something that involves only thetas, and we no longer have x's. So the expression that we have underneath our radical now is 1 minus sine squared theta. But we know by the Pythagorean theorem that 1 minus sine squared theta is the same as what? Cosine squared theta. So then this would give us the integral of the square root of cosine squared theta times cosine theta d theta. So we'll notice the reason this works so well with radicals is now we have the square root of a perfect square. So what's going to happen with our square and our square root? Yeah, they reduce out. So this is going to be cosine and cosine. So we're left with the integral of cosine squared d theta. This is an integral of the form that we learned how to integrate last time. So to integrate even powers of cosine, we use the half angle identity. So for this, we're going to use the half angle identity. So that integral becomes the integral of 1/2 times 1 plus the cosine of 2 theta d theta. And we can now go ahead and integrate that. So we have 1/2 times, the antiderivative of 1 is going to be theta plus the antiderivative of cosine 2 theta is going to be sine 2 theta divided by 2. And so now we've got to be a little bit careful because this was a definite integral. So what do we need to plug in? Our limits of integration, right? But the problem is our limits of integration were originally in terms of what variable? X. And now we have an integral in terms of what variable? Theta. So are my limits of integration going to be the same in my new integral? And the answer to that question is no. So we have to convert our limits of integration from our old variable to our new variable. So when we look at what we have right here, we have x is equal to sine theta. Well, this is the same if these are x values, then we're going to have two equations. We have 1 is equal to sine theta. And so when does sine theta equal to 1? Sine goes up, comes down, goes down to -1. So if we take the inverse sine, we'll get the same thing. So the inverse sine of 1 is equal to pi over 2. And what's our second equation going to be? Well, what was our lower limit of integration? 0 equals sine theta. So that's going to give us theta equals the inverse sine of 0, which is going to be 0, right? So our new limits of integration were from 0 to pi over 2, 0 to pi over 2, 0 to pi over 2. So when we put these in, we need to go from 0 to pi over 2. So now finally, evaluating our integral at these values, we get pi over 2 plus the sine of 2 theta. So 2 times pi over 2 is going to be pi. So sine pi over 2 minus 1/2, and we've got to plug in our 0. So 0 plus 2 theta times 0, so it was going to be 0 over 2. Well, it turns out the sine of 0 is equal to 0. So both of these terms, that is 0, that's 0, and 0 plus 0 is 0, and 0 times anything is 0. So that whole last bit is only 0. And what's the sine of pi equal to? So sine is the y value. If you rotate to pi radians, what's your y value? 0, right? Because it's at -1, 0 on the unit circle. So this guy is also 0. So all those terms are 0. We get 1/2 times pi over 2. So we get our solution is pi fourths. So the value of our integral is pi over So a couple of key things we really want to talk about. If we have limits of integration, you absolutely have to change them from whatever variable you started with into angles. This is a very common mistake that people forget. Otherwise, you have to back substitute, and in this case, it could be done. If we had our antiderivative, if we were trying to find it, so note, for an indefinite integral, we would have to back substitute. So our antiderivative was 1/2 times theta plus the sine of 2 theta over 2, right? But if we were trying to find the antiderivative, we need to get back to x's from theta. So there's a couple of things we're going to need to do to help us out. So we had our original substitution was what? X was equal to sine theta, right? And we need to get back to x's. So to get our first one, we can actually just solve this equation for theta by taking the inverse sine of both sides. So the inverse sine of x would be equal to theta, right? Because if we take the inverse sine of both sides of that substitution, that's what we would get. But we still have to deal with this piece. So for sine 2 theta, we need to use the double angle identity. The fact that the sine of 2 theta is equal to 2 times sine theta cosine theta. So if we substitute that in, I'm going to distribute my 1/2 in. So we have 1/2 theta plus 1/4 times the sine of 2 theta, which is equal to 1/2 theta plus, using our identity, we're going to get 1/2 times sine theta cosine theta, because the 2 and the 1/4 reduce to 1/2. So we need to substitute these things out. So we have that theta is going to be the same as this, and now this is where our triangle comes in. So we had the expression of this form, right? So that corresponds to this first triangle that we had in terms of our substitution. For our example, what was our a value? 1. So we have our triangle, but instead of having a squared, we're going to have just 1. So for us, a equals 1. So we get 1 minus x squared. So now we need to figure out what sine theta is. Well, on this triangle, what's sine by definition? Opposite over hypotenuse. So sine theta, we're going to end up with 1/2 times the inverse sine of x plus 1/2. And then our sine theta is going to be x over the square root of 1 minus x squared, because it's opposite. Oh, sorry, wrong thing. That's tangent. It's just going to be x, right? Because it's opposite over hypotenuse. So that's going to give us x over 1 times cosine, which is adjacent over hypotenuse, right? So 1 minus x squared all over 1 once again. So then putting all of that together, we get the sine inverse of x plus x times the square root of 1 minus x squared all over 2 plus c. And that would be the antiderivative, right? So then if you wanted to, you could then put 0 and 1 into that, the original limits of integration, and get the same thing that we got doing it by switching your limits. That will always save you a ton of work. So if you have limits of integration, always substitute them for the new ones. Otherwise, you're going to have to do all this work and then substitute in anyway and then simplify probably an uglier expression. So you're just making yourself work harder. So if we need an antiderivative or an indefinite integral, we're stuck. We have to do it this way. If we can change our limits of integration, we should, and do our integral accordingly. All right. Let's try our next example. So example number 2. Let's go ahead and evaluate this integral. So let's go take a look at our substitution suggestions. So we've got something of the form x squared minus a squared. So that puts us in row number 3 here in our table. So our suggested substitution is x equals a secant theta. So what is our a value going to be? So we have x squared minus a squared, and we have x squared minus 9. So this implies our a value is going to be 3, because 3 squared is 9. So then we're going to let x equal 3 times the secant of theta. So then our derivative is going to give us dx is equal to 3 secant theta tangent theta d theta. And then we're going to substitute all of this into our integral. So that's going to give us the integral of 3 secant theta tangent theta d theta over, we have the square root, and we have x squared, so 3 secant squared, 3 times 3 is 9, secant squared theta, take away 9. And now we need to reduce this. So we factor out our common factor of 9, leaving us with secant squared theta take away 1. And if we go back to our chart, secant squared theta minus 1 is equal to tangent squared by our Pythagorean identity. So this is going to be equal to tangent squared theta. So finally, putting all of that back together, in the numerator we end up with 3 secant theta tangent theta all over, we have 9 times tangent squared, but it's all in a square root. So what's the square root of 9? 3, and the square root of tangent squared is tangent d theta. And then we get some nice reductions. Our 3's reduce out, our tangents reduce out, and we're left with the integral of secant theta d theta. So if we think back to last time, what is our integral for secant theta. This was when we had that wild substitution for that we said to memorize, right? So this one is the natural logarithm of the absolute value of secant theta plus tangent theta plus c, right? So this is that crazy integral where you had to know what the answer was in order to make the right u substitution. So that gives us our antiderivative, but once again, we're in terms of theta. And we started out in terms of x, right? So we need to do our back substitution to get what we want. So we go back to our triangle, and this time we're using this triangle. Triangle number 3 with our a value, as we decided above, our a value was 3. So if a is 3, then this side is x squared minus 9 squared. So then our antiderivative is equal to the natural logarithm of secant theta. And what is secant by definition? Well, secant is 1 over cosine. It's the reciprocal of cosine. And what's cosine? Hypotenuse over adjacent. I would agree with that. So hypotenuse over adjacent gives us x over 3. That's this guy. Plus tangent, and tangent is opposite over adjacent. So that's going to give us the square root of x squared minus 9 also over 3 from our triangle, and plus our arbitrary constant. So this is a quote-unquote form of the correct answer. If you were to ask Wolfram Alpha or Maple or something else, they're going to simplify this down a bit. This is a perfectly good answer. Maple will take it, but we have a common factor of 1/3 in there, right? So we have the natural logarithm of 1/3 times x plus the square root of x squared minus 9 plus c, but then we have a product inside of our logarithm. So by the product rule for logarithms, if I have the logarithm of a times b, that's logarithm a plus logarithm b, right? So this would be the natural logarithm of the absolute value of x plus the square root of x squared minus 9 plus the natural logarithm of 1/3 plus c. But this is just a constant, so our constant of integration can just eat it, right? Because a constant plus a constant is just a new constant. So then we would have the natural logarithm of x plus the square root of x squared minus 9 plus a constant. Both of those are correct answers. I just want to warn you, especially with these types of antiderivatives that involve logarithms like this, oftentimes they will pull bits out and put it and hide it in the constant. Because if you have a constant plus another constant, it's just going to be a new constant, c. So this is a common technique that we will see. So if you check your work, say using Maple or Wolfram Alpha or something else on the internet, these are equivalent answers. So just keep that in mind, that they're going to be the same thing. All right. So now, all right. So in order to do this integral, we need to determine our substitution. So what we have looks like the radicand of this guy right here. So our a value is going to be 3, and we're going to have this. So it suggests that our substitution is x equals 3 tangent theta. So then dx is equal to 3 secant squared theta d theta. So we substitute into our integral, and we have 3 over 3 tangent theta squared plus 9 times dx, and our dx is going to be 3 secant squared theta d theta. So this gives us 9 times secant squared theta, and in the denominator we end up with 9 tangent squared theta plus 9 d theta. We factor out our common factor of 9 in the denominator, and we have a factor of 9 in the numerator. Pulling both of those out of the integral, they're going to reduce out anyway. Leaves us with secant squared theta in the numerator and tangent squared theta plus 1 d theta. So we go back and look at our substitution that we made, and we're always using the substitution to set up using that identity. So 1 plus tan squared theta is going to be the same as secant squared. So this gives us the integral of secant squared theta all over secant squared theta d theta. Well, anything divided by itself is just going to be 1, so we're left with just the integral of 1 d theta, or d theta. So then our antiderivative is theta plus an arbitrary constant. Well, we need to get back to our original x's, so what was our substitution? X equals 3 tan theta. So we solve this for theta, we divide by 3, we divide by 3, and we get x over 3 is equal to tangent of theta. So we then take the inverse tangent, so theta is equal to the inverse tangent of x divided by 3. So we substitute that back in, and our solution then is the inverse tangent of x divided by 3 plus constant. So that would be the antiderivative of 3 over x squared plus 9 is the inverse tangent of x divided by 3. All right, so let's take a look at example number 3. So example 3 is essentially this technique, but it's wearing a hat and a scarf. And what I mean by that is before we can actually do this integral, we need to make it look like one of the things from our form. Well, unfortunately, it doesn't look like that yet, but we do have a radical, right? So we have to do some algebra to help us. So whenever we have an irreducible polynomial underneath here, or actually any polynomial, we need to complete the square. So we have 3 minus 2x minus x squared, and we need to complete the square on this. So the first thing we need to do in completing the square is if our a coefficient isn't 1, we have to factor out a. So if a doesn't equal 1, factor a out of the x squared and x terms. So we're just going to leave our constant alone in this whole process. So our a is -1, so we factor out a -1, and that's going to give me x squared plus 2x. I'm going to write my parentheses and leave some space, and then I don't touch the constant. It just comes along for the ride. So now we calculate b over 2 and square it. So in our case, our b is 2. So we're going to have 2 over 2, which equals to 1, which makes squaring it easy. So 1 squared is equal to 1. And then we're going to, our next step, step 3, is we're going to add 0 inside the parentheses. And in this case, we're going to add 0 in a very strategic way. We're going to add 1 and subtract 1, where we're using the value b over 2. So this is always going to be b over 2 squared minus b over 2 squared. Well, the reason we have to do it in the form of 0 is the only thing you can add to something that doesn't change it, right? So if I add 0 inside my parentheses now, I'm going to have x squared plus 2x, and then I'm going to have plus 1 minus 1, and then on the outside I have 3. This will always create a perfect square trinomial. And in fact, it will always factor into x plus b over 2 squared. So we're going to get -1 times, and then parentheses, if we factored x squared plus 2x plus 1, that's x plus 1 squared. But then I have this extra -1 plus 3. So then I distribute and simplify. And that's going to give me negative x plus 1 squared. -1 times -1 is plus 1 plus 3. So this gives me, and I'm going to write it in kind of a funny order, 4 minus x plus 1 squared. So after doing all of that, I now have the integral, because I completed the square on the denominator, of x over the square root of 4 minus x plus 1 squared dx. So this looks closer to the form of the integrals that we've been doing. In fact, we can exactly turn it into one of the trig substitutions by making a u substitution. So what u would we need to substitute at this point? X plus 1. So if we let u equal x plus 1, then du is equal to dx. We're also going to need this, so -1 minus 1, we get x is equal to u minus 1. So substituting all of that into our integral, we get u minus 1 over the square root of 4 minus u squared du. So our x became u minus 1, and our x plus 1 became a u. So now we're one substitution deep, right? We've substituted u's, but now this is of the form 4 minus u squared. So if we go and look at our substitution list, I have a constant minus something squared. So what row does that put me in? Row 1, right? So what's my new substitution going to be? Yeah, u is going to be equal to 2 sine theta. So now we do u equals 2 sine theta, and our du is then going to be 2 cosine theta d theta. So we substitute all of this into our integral. We end up with 2 sine theta, take away 1, over the square root of 4 minus 4 cosine squared theta times 2 cosine theta d theta. So we simplify some of our stuff up again. So this is the square root of 4 times 1 minus cosine squared theta, which is going to be the square root of 4 times sine squared theta, which is going to give us 2 cosine theta, which is very nice, because now when we substitute that into our integral, we have 2 sine theta minus 1 over 2 cosine theta times 2 cosine theta d theta. So these and these reduce out, and we're left with the integral of 2 sine theta minus 1 d theta. So now we integrate. The antiderivative of sine is negative cosine, so we get negative 2 cosine theta, and the antiderivative of 1 is theta, so minus theta plus c. But now we've got to start our journey backwards, right? Because we started with x's, and we're at thetas, but we had a u substitution in between, so we have to back substitute twice to recover our original variable. So our first substitution is u equals 2 sine theta. So we grab our triangle. So our triangle is going to be this guy right here. And so this was 4 minus u squared, and that makes this u, and that would make this 4. And we had the substitution u equals 2 sine theta. Sorry, that's not 4, it's 2. So we could solve this equation for theta, which we're going to need. So we divide by 2, we get u over 2 is sine theta. So solving for theta, theta is the inverse sine of u divided by 2. So now we're finally ready. We have negative 2 times cosine. And what is cosine? It is adjacent over hypotenuse. So cosine gives us adjacent over hypotenuse. So we're going to end up with square root of 4 minus u squared over 2 plus, minus, theta, and theta we figured out over here is going to be sine inverse of u divided by 2 plus our arbitrary constant, right? But now we don't want u's. What do we need to get back to? X's. So what was our original substitution? U is equal to x plus 1. So u equals x plus 1. So we finally substitute that back in. And we simplify a bit first. So we have 2 and 2. They reduce out. So that gives us the negative square root of 4 minus, and our u is x plus 1 squared, minus the inverse sine of u over 2, and u is x plus 1 over 2 plus c. So that's our antiderivative of that original integral.